I'm very excited to be here because Papers We Love has just always been a really good community to discuss ideas and to research papers and do it in just a fun way. So I'm very honored to be speaking here. So my name is James Long. I'm a web and iOS contractor under my company Shift Reset LLC. I used to work for Mozilla for about 6 years on developer tools and other projects. I consider myself a PL nerd with an attraction to Lisps, although more recently I've been sort of interested in the ML family of languages. A recent project that I built that was successful was Prettier, which many of you may know. It's a JavaScript code formatter, sort of similar to Go format. And it's been very widely adopted in the JavaScript community, which is pretty cool. Sorry. So I'll be honest. I'm not really somebody who prints out a couple research papers at night, and grabs a beer and sits down and falls asleep with papers all over me. I don't read papers that often, but I still love papers because even so, when I look back at moments in my career where I really grew as a programmer, many of them really happened because of papers. I'm also very passionate about taking ideas from the deepest parts of research and pulling them up into real applications. It's very important to me to be able to at least read papers to have a pulse on what's going on in that world. Because I think some of the best things that can happen when you can do that and apply those ideas. That's exactly what happened with Prettier. So I can think of 4 times when I was stuck on a problem and I discovered a paper to help me through it. Not only did it help me solve a problem, but I gained deeper insight about computing and ways to approach those problems. So I'm going to try to explain all of those papers in this talk. This is why it's a little bit different talk than I'm normally used to, because I'm going to be jumping around to 4 different topics that aren't really related. So I know everyone just ate lunch, but hopefully this will be fun. And I will also talk specifically about what I learned and how each paper influenced me. Okay, so let's start all the way back with college, James. In 2006, I had to graduate. I had to write a research paper, sort of like a very small thesis, and it was supposed to be something in computer science. Most people chose something purely in the realm of programming, sort of like data structures or databases and stuff like that. But I was really interested in graphics programming, and so I chose to study techniques for real-time rendering of the sky. Now, it turns out that most of my paper was about math instead of programming. So even though it was very technical, I don't think my teacher even really knew how to grade it. Like, he just gave me a B+, and that was just kind of like he did that because it looked good, but he didn't actually understand the math. So I guess that worked out. Yeah, so I wouldn't be so brazen as to talk about my own paper at a Papers We Love conference. The first paper I'm going to talk about is the paper that it was based on, which is rendering outdoor light scattering in real time. Now, I know that the title of my paper is basically the same with a few words moved around. I wasn't very clever back then. So this paper was by Hoffman and Preetham, published in 2002. This paper is a bit different than the rest of the papers I'm going to talk about, because it's about computer graphics. It focuses on bringing realistic atmospheric rendering to real-time simulations. So my challenge was to get the techniques of this paper working in a real app and write my own paper about that. So I implemented it for my paper, and I got it working. So these are screenshots from my app that I created that I was able to implement. And these are all completely real time. You can walk around in this world. You can adjust parameters of the sky. So back then in 2002, which is when the paper was written, I wrote my app in 2006. Back in 2002, the hardware was very limiting. And so this was a very cool real-time technique because this was right around the time that shaders were starting to go big. This is right around where shaders were finally starting to actually be in the mainstream, if I have my history correct. But we were finally able to start doing stuff like this. And so this was one of the first papers, or one of the early papers, to start really leveraging shaders to do this kind of stuff. Okay, so just a little background. In 1871, J.W. Strutt, or Lord Rayleigh, published equations that model how light is scattered by small particles, which make up the majority of the atmosphere. And this answers the classic question, why is the sky blue? The fundamental thing is that shorter wavelengths are scattered more than longer wavelengths. So why do we even see color in the sky except for the sun? Like, if you look up, why do you actually see blue all around the sky? Why don't you just see black and then just like the sun as a disk, which that's actually what happens if you're on the moon. But down here on Earth, we have the atmosphere. So light is hitting the atmosphere at a fairly uniform direction, and the atmosphere is scattering that light, and so it scatters into your eye. So the reason it's mostly blue is because shorter wavelengths are scattered more than longer wavelengths, and so violet and blue are on the shorter spectrum. And you don't see violet for some other reason. Blue is like a stronger color or some other phenomenon. This is also the same reason why objects in the distance appear slightly blue. Think of mountains that gradually get more blue the farther away they are. This happens because the farther away an object is from you, the more light is scattered into your eye from the sunlight. So there's more atmosphere between you and the object to scatter the sunlight into you. And not only that, there's actually an extinction factor where the color of that object is actually being scattered away. So both of those effects happen. So there are two things that we need to worry about: rendering colors of the sky and also aerial perspective, which tints objects far away. Luckily, if our implementation simply models how scattering just works, we get both of those for free. And this is in contrast to earlier papers, which they couldn't do per pixel shader work, so they couldn't actually implement in real time how to model this. So they did approximations, and so they had to treat aerial perspective and the actual sky color differently because they're sort of faking it. But we're just going to implement this in the shaders so we can actually approximate how it works, and we just don't have to worry about the difference. Okay, so to do this, we need to model three effects: absorption, outscattering, and inscattering. Absorption is the effect of a particle absorbing light rays. It simply stops the light. Outscattering is the effect of light bouncing off a particle away from your eye. So it's sort of similar to absorption. And inscattering is the effect of light that was not going to come towards you, but it bounces off a particle towards you. So there's both light that is scattered away from you and towards you. And this paper provides equations for calculating these terms so they can be implemented by a graphics program. These are absorption and outscattering. I don't have time to fully explain the math, nor am I honestly sure that I could, but I'll try to summarize. Absorption and outscattering can be treated the same way in our case. We don't really care if a light ray has been absorbed or scattered away. We just need to ignore that light. What these equations are saying is you take the initial color of an object and you exponentially attenuate it over the distance to the viewer. So the farther away an object is, it exponentially gets more skylight and less color of the object. So for each pixel, we generally know the point in space that it's at, and so we can calculate the distance to the viewer. And for every single pixel, we know that distance, and then we can do we can run this model. So inscattering is a lot more complicated, but it's not as complicated as this math makes it seem, and I definitely couldn't explain this math. And it's sort of hard to read out of context because most of this is just predefined variables and functions. But the main thing that you need to understand is the phase function. The phase function approximates the amount that light is scattered by a particle. It takes the angle of the incoming ray and returns the amount scattered at that angle. In Rayleigh's original work, he proposed this equation to approximate it. So this is the phase function, 1 plus cosine squared theta. If you think of a ray entering from the left, the phase function approximates how light is scattered at each angle. So the most is scattered forwards and backwards, and the least is scattered at 90-degree angles. To put this into perspective, here's how it would work in our program. You have the sun position and the viewer position, and you need to calculate the color of a specific pixel. We generally know the position of that pixel in world space. So all we have to do is calculate the angle from the sun to the viewer, and then we run it through the phase function, and that gives us an approximation for about how much light is scattered at that point towards the viewer. So this would be about in between like the minimum and the maximum of light scattered, because it's about 135 degree, and it's like in between 90 and 180. So there are a lot more things that you could factor in. Particles are different sizes, and different sizes have different effects. For larger particles, they actually have a different phase function, which is me-scattering, and that's a whole different thing. The distribution of the particles of the atmosphere may not be constant. Right now, we're just assuming that it's a constant atmosphere. And these things definitely complicate things a lot more. But even simple versions of these equations can produce pretty pleasing results. The best thing about this paper is that right around 2002 was when shaders were taking off on graphics cards, and this allowed developers to implement all of this sort of stuff with ease. In previous papers, they were forced to do all sorts of other hacks. So after presenting the math for modeling atmospheric scattering, the paper ends by providing much simpler equations that can be implemented in vertex and pixel shaders. These are simple because it assumes a constant density atmosphere and relatively flat terrain, which just gets rid of a lot of the complicated math. So all of the variables here are super straightforward to calculate. As the angle to the sun, there's 2 different constant scattering coefficients, and a few other things. It's basically some additions, divisions, and cosines. Now, when I was implementing this, I was back in college. I had done a decent amount of programming, but nothing on this scale really. And this blew my mind. I mean, I remember feeling super overwhelmed trying to pick through all of this. And even though I didn't understand much of the paper, once I saw the conclusion, which was where the simple stuff was, maybe they should have put that at the front. I was like, oh, like that's super easy. Why do they have to complicate it so much? But I saw this and I was like, yeah, I can just translate this into a vertex shader and get this to work. And I got it working. It was amazing. I could walk around in this world that I created. And so, yeah, that was cool. So what I learned is that, first of all, it's very hard to make realistic graphics. So after that phase where it was amazing, then I looked at this and I was like, well, that actually kind of sucks. Like that's not really realistic at all. So it's very hard to make realistic graphics. This was also the first time that I experienced the work of translating abstract ideas, in this case math, into executable code, which is surprisingly difficult. If you're an experienced programmer, you do this daily. But at the very beginning of the process, that's a hard skill to learn. It's not something that's intuitive or we learn as a child. It's something that takes a lot of work to learn. So it was interesting to go from this looking at those equations and learning how to filter them down into something that could become actual shader code. And in terms of how it influenced me, computers are amazing, and we can create stuff from nothing. And also, don't give up if you don't understand something at first. Once I found a piece of the paper that I could finally understand, I got something working, and then from there I could work backwards to the paper and understand more and more. All right, so that's that paper. This paper was a bit different than the other 3 papers I'm going to talk about because it was heavy on math and computer graphics. The rest of the papers are mostly about compilers, so if you don't like math, don't worry, there's no more math. The next paper is called An Incremental Approach to Compiler Construction. This one came out in 2006, and I think I read it in about 2007, about a year later after my graphics project. And I was just starting to get interested in compilers and scheme and more niche languages, but I was still very intimidated by all of it. This paper was written by Julio, who created Icarus scheme, and the paper describes his approach to creating that scheme. Icarus is interesting because it compiles straight down to native assembly, so it doesn't use I can't remember if LLVM even existed in 2006 or 7, but it just compiles straight to a platform assembly. And so it does that to take advantage of the native platform's capabilities and also for speed. It was also very interesting because it was self-hosted. So it was the entire thing was written in itself with very, very little written in C, very little of the runtime. So compiling to assembly made Icarus the Icarus compiler itself fast because it was self-hosted, so it was able to, every speed improvement that it made, it was able to take advantage of. So to somebody new at compilers, this was very intimidating, but Julio used an incremental approach to develop this, which made it a lot more accessible. And this paper outlines 24 explicit steps to reproduce a compiler with many of the same features as Icarus. And each step builds on the last, and each step is very small and incremental and approachable. It sort of reminds me of this talk by Guy Steele called Growing a Language. He shows that when you start with very simple terms, that the absolute minimum that you need to start talking and actually doing stuff, then you can build those up and combine them in different ways and create higher level abstractions. And then you can take those abstractions and continually build on those. This is a super interesting talk that if you haven't seen, you should absolutely watch. So here's the very first step in the paper. Write a compiler for a language that returns a fixed size integer. So our entire language is just numbers, it's just integers. That's it. And this is how the paper approaches it. Let's write a small C function that returns an integer. Now, we don't know how to do this yet. We don't know assembly code. And so let's just write a C function which returns an integer, returns 42. Let's compile it out and look at the assembly. And we can learn from the output and just see what we need to do. This is a really fun way to learn. So the only part that really matters to us is the two lines at the bottom here, where it moves the constant 42 to the EAX register, and then it returns. So now that we have that, let's implement our compiler. Here it is. It's 3 lines. This is a compiler for a whole language, and it's only simple because our language is literally just integers. And the emit function is just a function that you can assume how it works. It just emits strings, and it might interpolate values into the string if there's a squiggly A. This might seem trivial, but this is a great way to break down barriers and make things like compilers more approachable. I remember feeling instantly connected to this paper and super excited that I might actually be able to follow it. I didn't really have to work at finding which part of the paper to connect. It was organized in a way to help me learn. If you contrast this with the graphics paper, I was like, what the heck is going on? 2 weeks into it, I finally found the end, and then was able to understand it. So note that we are initially relying on the host scheme to provide functionality for parsing the scheme syntax. So scheme provides a read function, which takes a string and returns and it parses it into a data structure. So these are a bunch of lists. These are just nested lists. That's all they are. It's sort of like JavaScript's JSON.parse. And because scheme syntax is so simple, it can be represented as these lists. So we can just use the host scheme's read as the parser. However, since parsing lists is pretty easy, the paper does go on later into a later step to show how to implement this read function in our compiler. So the next step in the paper is the ability to handle different constant types. So we've been dealing with fixed sum integers so far, but you also want characters, maybe even floating point, booleans, null, and all these other kinds of variables. Well, maybe you don't want null. But we can encode this type of information by dedicating some of the lower bits of the machine word to it and converting that constant value at compile time to the shifted value. And so this is our compiler now. Say that you're compiling a program that is the integer 5. The compiler is going to take this, it's going to convert it into an immediate representation, which it says this is an integer, I'm going to shift that value, so it shifts 5 over a few bits, marks the type of that as an integer in those lower bits. And then we can go on to implement characters and booleans and other types like this. And so here, So I'm going to keep walking through some of the early steps to show how quickly but clearly this moves. But it's awesome. I'm not going to go through all 24 steps, though. So far, all we have is the ability to return a single value. The next step is to implement a basic function call to actually do something with it. We will only implement unary built-in primitives, single argument functions provided by the system. So this is our compiler now. It turned into a recursive function because now we need to recursively handle nested expressions. If it's an immediate value, it emits that assembly. Now, if it's a primitive call, we get the name of that primitive call. And here we're going to implement an add1 primitive call. What we're going to do is we're going to compile the expression that we're adding 1 to. And now that is left into the EAX register, because that's like the return register. That's always the register that has the value that was previously executed. And then we're going to emit an addl, and we're going to just say addl a constant 1 to EAX. So we're just going to add 1 to whatever it is in the EAX register. So now we have a function add1 that we can call on integers. And you can also implement a bunch of other things this way, too. If we have characters and integers now, now we can do type conversion. So we can say integer to char to integer, null, 0, not, whatever other unary primitives that you need. So unary primitives are easy because there's only one value that we need to put somewhere, right? So what about binary primitives? So here we have a plus and 2 expressions. We can't rely on just a value putting it in the EAX register because we need to put these 2 expressions in intermediate places that the plus operator can work with, right? So when you start adding more arguments, we need to put multiple values somewhere. You need a stack. So a stack is a contiguous array of memory locations. And we have a pointer to this contiguous memory in the ESP register. The return point is stored at the base of it, and we're free to use locations above it for our intermediate values. So -4, -8, -12, and it's based on 4 because that's our word size. So every value is 4 bytes. And the compiler tracks the current index into the stack. So this is what our compiler looks like now. Now we have that extra SI parameter, which is the stack index. This is an example for how you could implement binary primitives. Now, we've pulled out the code that just compiles the primitive calls, right, into this function, and we're just going to focus on that. So now we are going to implement the plus operator, which is a binary primitive. What we do is we compile out the first operand, and that exists in the EAX register. We move that value onto the stack, which is that, move L EAX to the squiggly A ESP. And then we compile the second operand, but we increment or we move the stack pointer. So see how in the second emit expert, it says minus SI word size. We move the stack pointer by word size because we put something on the stack. So whatever that expression is doing, we don't want it to mess with the value that we put on the stack already. So when that returns, now we have that value, which is in the EAX register. And then we say add L, the value that we put on the stack with EAX, and we are able to add two values. This is simple because we're only handling two arguments, but you can implement a lot of binary primitives this way. So now that we have a stack, local variables are pretty easy. The compiler passes around an environment in addition to a stack index. When a new variable is introduced, you compile the expression, you push it onto the stack, and you add that variable to the environment with the stack location. When a variable is used, you get the stack location from the environment, and you read it from the stack, and that's it. So here's the code for how you could implement local variables. It's getting a little long for slides, so don't worry about reading all of it. I'm not entirely sure if you can even see it. But there are three main points to look at. One is this is where if a variable is used, it looks up the stack index from the environment, and it just reads the stack. Here is where it compiles the value of a variable, and then it moves that value onto the stack. And here is where the environment is extended, and the new variable is extended with the new variable with the stack index that it has, and the stack index is moved itself. So we've pushed something onto the stack, tracked it in our environment object, and then it can be used later to look up that variable. So this was the 5th step out of 24. Obviously moves super fast, but it keeps it simple enough to be approachable. It goes on and on. I'll summarize a little bit of the rest of the paper. The next big missing piece is heap allocation. And the paper describes a simple way to do this. You basically pre-allocate one large contiguous array at the beginning of the program. You pass that heap pointer into your program at the entry, like when the program starts, you pass it into the entry point. And then to allocate, you have whatever number of bytes that you need to allocate. You increment the heap pointer by that number of bytes, and then you are able to pass pointers around into that heap. So that's it, right? I mean, obviously there's a glaring omission here, which is garbage collection, and it's just going to keep allocating stuff with ever deallocating it. But the whole point is that this actually gets us a heap that we can run, and we can move on to more interesting features. It's pretty easy to come back and implement a much more robust allocation strategy. So now that we have a heap, we can move on to more powerful things like user-defined functions and closures. We needed heap allocation because closures make closure values outside of their scope, and so it creates this runtime closure object that we need to create, and so you needed a heap to do this. But now we have that, even if it memory leaks. And it goes on to show how you can use macros. It doesn't really go into macros. It just uses the host scheme's macro system. But I think this is a super interesting technique where you have this very simple language that compiles out to extremely fast code and simple code, but then you have a macro system that is able to leverage some other more powerful schemes environment to do things at compile time. So you let the user extend the syntax into all sorts of crazy things. It goes on to show how foreign function interfaces work. You can call native C functions, I/O, and a reader. So now that we can read source code and we can even parse it, and we have our compiler, this really is building towards self-hosting. And now the paper doesn't really actually go this far, but now that we have all of that, we can do this. This means that the language you are implementing becomes powerful enough to run the compiler itself. You can then point the compiler to the compiler source and generate a new compiler from it. If you've never done this before, I highly recommend it. You kind of feel like you're king of the world after that first self-hosted compiler. But then you kind of want to shoot yourself when you implement a new feature and your compiler can't compile it. So it's a fun cycle. Anyway, what I learned, having to implement a language from scratch without relying on any of the virtual machine or environment teaches a lot. You really have to learn that you have to build everything from just raw bytes. I remember trying to implement closures, and it was probably it really helped me understand the costs of closures at runtime and how closures actually work. In general, it just made me appreciate all of the work that virtual machines and JITs do. In terms of how it influenced me, it really influenced me in a big way. And I actually think about this paper a lot these days when I'm faced with a complex problem that I don't understand. I remember that very first thing that it does, which is it writes that 3-line C function to compile out and just learn what it compiles to, and that way it uses that technique to teach. You can teach yourself by just doing things. So really, I think about this a lot when if you're really stuck on something and you don't even know where to get started, just start writing something, and then that will start your process about learning stuff and give you more ideas as you go along. When I was younger, it really helped me believe that I could actually do this, that I could actually do the hard stuff, and it's okay to ignore the complex details at the beginning. Okay, so the next paper is about compilers as well, but for a much different reason. It marks a time where I was intensely searching for a solution. I think this was around 2002. I enjoyed blogging a lot, and I really wanted to write tutorials with an interactive JavaScript debugger right there in the browser. So no extensions, just literally was able to write this interactive JavaScript debugger where you could stop execution. This is clearly a tall order. I did not realize this at the time. But basically, if you have this code, I wanted the ability to somehow stop the execution right here. And I just didn't really know enough to know what I was getting into. I was willing to compile this into whatever JavaScript I wanted, as long as it could be run in the browser without any extensions or anything. I figured there was something I could compile it to make this work. So here's a fun hack I tried at first. I'm going to start this program. It's just a quick demo. Oh, I'm sorry. I have to Shift Fn F1. Cool. All right, so here's a fun hack. So I started a server. What this is these are 2 iframes, and I've loaded a program in the left one, and I can click this run button to run the program. And so let's see. Let's run the actual program. What the program does is it just outputs a bunch of stuff to the screen. 0 through 14, hello. It can just keep doing this. It creates a div and it appends it. What I was wondering is, could I have this pause function that will pause? So let's say, on the 6th iteration, pause. How I implemented this pause function was I created an XML HTTP request, and I did a synchronous XML HTTP request to a server. And I wrote a server that never responds to that request. And so I can literally run this, and it pauses. OK, the first problem is that nothing outputted. Turns out Chrome just doesn't actually flush the side effects, literally just pauses the entire world. But I can't even press any of the buttons. In fact, I can't even refresh. Like, Chrome literally just is hosed. I just have to close the page. I actually have to run this in nightly, Firefox nightly, to get this to work. So let's see how nightly does Firefox. So if I run this, oh, sweet, so I can actually see it at least. The buttons are still hosed. Can I refresh? I can't refresh in Firefox either. So how could I get this to work? So I thought, like, what if I open a new window? Because it can't stop me from that, right? And I created a different page, which has a continue button. What this continue button does, when I press this, it's going to hit my server and say, OK, respond to that request. And so now when I hit continue, it continues. And actually, this is kind of cool. Like, now I can pause in every single iteration, maybe. So I can say run. Yeah, that's the first one. Continue, 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 continue. It's like a stepping debugger, right? For some reason, it actually always stops around 6 or 7. I have no idea why. Like, I'm pressing continue. It's like the synchronous, like the browser is just hating me for doing this to it. So yeah, so clearly that hack was a horrible hack, but it was fun. So yeah, so my next idea, which was a little less stupid, was called YPS, which I called yield passing style, which makes no sense because you're not passing anything around. But generators were starting just to become available in JavaScript engines. And so I was thinking, well, a generator has the ability to pause a function at any point in time. If you're inside a while loop or inside an if, it just pauses. So is there any way that I can leverage that? Because I want that, but I want it to be a deep pause. So what I did was, if you take this code, what if you injected yield statements in every single expression, and then you have to run this in your own sort of virtual machine thing? And this quickly died because the performance of this was just horrific. So I went about searching for something more robust. And around this time, I realized that what I was basically trying to implement was continuations. And someone pointed me on Twitter to this paper, Exceptional Continuations in JavaScript. Now, by this point, I'd understand this problem so well that just like instantly I knew that this is what I needed to do to get this to work. This paper shows how to implement continuations in a language that compiles to JavaScript. So continuations are difficult to implement, even more so in dynamic languages like JavaScript that run in a JIT or virtual machine. One option is to convert to continuation passing style and everything, but then you're like dealing with a whole different form of code that doesn't run well at all on JavaScript engines. And we just don't want to miss out on the excellent JIT capabilities of modern JS engines. Because I was really just wanting a debugger and not really first-class continuations, I didn't really care about the costs of creating a continuation. So when you're implementing when you're implementing continuations, you usually make a trade-off, where it's either you take a slight perf hit across the board, so everything is actually using continuations underneath. So there's always a continuation object there for you to capture, so it's super cheap to capture them. Or you optimize normal code, and creating a continuation is super costly because it has to like traverse the stack and copy it and stuff like that. So what this paper does, it shows a technique with the latter trade-off. Creating continuations is super costly, but the code itself runs pretty well. So the first part of this paper shows a basic idea. It summarizes existing work, and it shows two forms, suspend and resume. This is an example implementing a sleep function with it. It suspends the current execution and gives you a resume function to resume it. Now this is a deep suspend, so all functions on the stack are paused. This means that all functions need to be instrumented to handle that. All functions need to be instrumented so that they can save their state and be restored later. So let's first look at suspend. Suspend does is it creates a special type of exception called a continuation exception. It keeps track of the handler that's waiting for this continuation, and then it throws it. So that's how this whole system works, is it uses the exception system to signal capturing a continuation. Now let's look at the necessary instrumentation. If we have this function, we need to capture all of this state. So here's the first pass. This is only half of it. This is just the suspend code. It's a little verbose, but it works. First, we wrap everything in a try-catch. And in the catch, we check if it's a continuation exception. If so, we create a frame object, and we store all of the values of the local variables to that frame object. And then we push that frame object onto the continuation and rethrow it. So every single function in the stack is going to catch this, capture its frame, rethrow it, catch it. So by the time it gets to the top level, we're going to have a whole list of frames. Another thing we do is we start keeping track of at what point of code this is running. So you see the index variable, which is set to 1 and 2 right before it invokes f and g. We're keeping track of which part of the code is running, because when we resume it, we need to be able to jump somewhere. Now, we haven't transformed it so that we can jump yet, but we're just at least tracking it. So the next part is the part for resuming. So this is the same function. The main thing we've added is that big block at the top for restoring state. When resuming, we set a global restore.doRestore flag, which switches the functions into this restoration mode. And it pops a frame off the stack, which is our frame, and it resets all the state, the local variables, the index of the code that it's currently running, and everything like that. We've also now fully transformed the code into a state machine, which is this switch statement. This lets us jump to any part of the code that was suspended. So the place we should jump to is stored in the frame, and then we set that to go to, and the switch statement will switch on go to and flip to that piece of code. So that's the basic idea. You save your state, you can restore it, and you divide up the code so that you can jump to it. So here's our original code on the left, fully transformed code on the right. It's a little ridiculous. But that may be okay if you just don't care about code size. And for me, I actually didn't at all, because I was just wanting to have like short snippets of code as tutorials that you could run and step through, and it was never downloaded over the internet or anything like that. And this trade-off is intentional. This large, complicated code block is catered to play nicely with current JavaScript engines. We get to reuse all of the native stack environment and things like that. And we've only added a small amount of overhead, which is like the switch statement and some temporary variables and a couple other things like that. So the performance of it, the performance hit of normal code is actually not too bad. So there are a few tricky things that we need to address. One problem is with closed over values. Here's the function g, which closes over x and y. We actually want to leverage JavaScript's native scopes for performance, but it causes this problem. When the function suspend call is invoked, and that let's assume that suspends us, when f is resumed, g is going to still point, g is going to be set to the function that was saved, but that function is still going to be closed over the old values of x and y, or the old kind of references to x and y. So even though we set x to 3 after it's resumed, G is not going to see that mutation, and so it's going to print 1, 2, even though it should print 3, 2. The paper solves this by boxing all non-constant escaping variables. This way, even though the references to the box are not kept correct across restorations, the value in the box will still be seen across them. All right, so far we've been talking in terms of suspend and resume. If you want full call CC, there are a few more things that we need to think about. We're most of the way there, but there are still a couple other problems where the variable references get lost, sort of similar to what you just saw. The paper goes on to show how we would generalize it into full proper call CC by making sure you always keep those references. It also describes some other optimizations and stuff like that. So let's talk about how to actually implement this, though. If we need to transform code into a state machine, isn't that hard? Take this example code, right? We want to break here, but there's a for and if. How do we actually be able to jump arbitrarily into that? Well, the thing is that we need to invert it into a state machine and have control over it. Luckily, right around this time, a project called Regenerator was released, which actually did this state machine transformation. This compiles ES6 generators to ES6.5 code, and so it has to do that, because there might be a yield in the middle of all this, right? So I was able to take this and I forked it, and I implemented it to expand everything, so every single expression is a jump point in the state machine. So if we have this function with a while loop, this is the output of my compiler. You have a while loop, which infinitely executes. You have a switch statement with a next. Next is the jump point for it to next to. And so case 0, if we're not stopping, we jump to 3, which calls update with entities, which jumps to 7, which jumps back to 0. So that's the while loop. So we are re-implementing all of the control flow constructs. So here's just a quick thing of it working. I was able to pull this up, and the page is a little busted, but it still works. The cool thing about this is that this was my proof for, I lost my cursor. This is my proof that because my main concern was I wanted to do sort of graphic stuff. Oh, you're right. Oh, thank you. That was close. So my main concern was performance, because part of the thing that I was thinking of was doing like 2D or 3D graphics tutorials. Let's see if this works. So the resolution's a little messed up. Let's see. No, it's better. So I wanted to make sure that I could actually run simulations and have them be interactive at 60 frames per second. So I have all of this code here, which implements a cloth simulation. It's about 230 lines of code. I can run this, and this is all compiling out to the continuation stuff and running it, but it's still fully interactive. So the JIT is able to just eat this and still make it very fast. But what's super cool is that I can even come down here and prove that this is running in my machine by setting a breakpoint right here. So it paused, and I can step through the code. So this was sort of my goal. So this was super cool. It looks like this actually works. In fact, I can keep playing this. If I interact with this some, keep playing with it, I can step over every single frame and see it move over a single frame. So I have complete control over what's going on now, which is pretty fun. All right, now since I came this far, I thought that I should go ahead and expose continuations as first-class values, right? Because it's just super cool. I created a built-in call CC function, and so now you have what scheme has. I'm not going to explain this a whole lot. If you know about continuations, you know how this works. I'm transporting the value 5 back into where the continuation was captured. And the key here is that when you call x, when it's a continuation, that function call never returns, which is just how full continuations work. Delimited continuations are really the best abstractions, and we saw Kenichi talk about that earlier this morning. I thought about implementing delimited continuations in this, but I just didn't have time. So my project is on GitHub if you're interested in this. It was pretty fun to implement. So what I learned, first, try to be aware of how much work you're about to put into a useless side project before you do it. Yeah, so way too much time. Also, synchronous XML HTTP request really is that terrible. And third, I just learned a ton about implementation details of languages and trade-offs that need to be made. And how it influenced me was spending all this time thinking about continuations and how to implement them really has helped me more easily pick up more powerful ways of programming and computing. Like algebraic effects and things like that are things that I think are super interesting. And now that I think continuations are one of those things that's just sort of good to learn because it really breaks down a lot of stuff. And it's made me appreciate the power of having control over control flow, even though it's only useful sometimes. Okay, so hopefully you're still paying attention because kind of jumping around here. Just one more paper to go, and this last paper also helped me in a time when I was stuck. More recently, in last December, I just got so tired of manually formatting my JavaScript code. And I think all of you all know what happened. I set out to build an automatic formatter. I knew that for this to work, it needs to take line width into account. It just has to. I looked at all of the existing current printers, and none of them did that, and none of them were able to produce actual real-world code that people were willing to work with. They all just printed certain types of code on one line. So there's so many styles of code in JavaScript that we have to take line width into account to know when to break expressions and things like that. Interestingly enough, Go format, I believe, does not do that. And it seems to be widely adopted. Like, people seem to love Go format. My only theory is that Go style of code just doesn't lend itself to code that is horizontal. It lends itself to vertical code. And so people are just OK with a more fixed syntax in there. But JavaScript has a crap ton of syntax, and we can't do that. The best printer that I found was in a project called Recast, and it did try to take the width of expressions into account, but its measurements were crude, and it didn't really work out in practice. But it had a ton of code for walking through the AST and handling things like comments. So it was a really good start. So I forked it and started searching for a better solution for how to measure the lines. After banging my head on the wall for a little while, I saw that I needed to implement just a completely new system for measuring the lines, and also even a new system for how to express how things should be formatted. So that means I did have to go into Recast and re-implement each node handling code, but it was still useful to base it off of Recast because it just had a ton of other like grunt work done already, like handling comments and stuff like that, which is really ugly. So Recast. Recast is the only reason why I was able to do it in just a few weeks. So for the measurement system, after poking around a little bit, I found this paper, A Prettier Printer by Philip Wadler. And it turns out there's a whole bunch of research on pretty printing. And this paper shows a very simple and elegant way to implement it. This paper uses Haskell for its examples. And I don't really know Haskell, but because I hit this problem in a real application and I had thought about it for a little bit, I knew the problem well enough to be able to read it. In fact, once I figured out the basic terms, it all started clicking. And within a few hours, I really understood how the basic algorithm should work. This is probably the best case of going from, I have no idea how to do this, to finding a paper and then a few hours later saying, oh, I should just do that. I mean, and that's why at the beginning of my talk I was saying I love being able to read at least the gist of what a paper is trying to say so that we can pull it out into more real world code. I think more people need to do that. This paper is really the reason why Prettier is successful and why we're able to handle so much types of syntax. And so therefore, Prettier was born. And this was so cool. How many of you all have used Prettier in here? That's cool. A little disappointing, to be honest. So I will show you why it's cool. Maybe most of you all don't use JavaScript. I don't know. Let's see. I was already actually working with this code. So let's say that I have this code. Does this work? Yeah. Let's say that I just wanted to change this around, reprint it up. Oh my goodness, man. Thanks, guys. Or y'all. All right, let's say that I have this code. Let's say that I'm working around with it really, really fast, and I wanted to change this to just this function call, and I'm just kind of making stuff up right here. Oh, no, that didn't work. Yep, there you go. Then I wanted to say in the map node into I'll just do this into an object. So basically, I can just type the code and just reformat it, and it just was going to reformat it however it worked. I don't have to care what I'm typing has actually changed the syntax around it. So that was just a very quick demo. Because when you start working with it, it really is enlightening and helps you focus. So a brief overview of the paper, because I'm running out of time. This paper starts by considering the case where each document has only one possible layout. So, and it gives you these operators to define that layout. There's a concatenation operator, nil, text, line, nest, and layout. These all work on documents. So we can use these operators to define a simple layout. So if you had, let's say you had a tree data structure, here's how you might implement a layout for that tree data structure. You would use these operators to compose them into this layout system. So this recursively goes through the tree, and you can see that it's concatenating the result of show tree with a comma and then a line, and then recursively going into show trees. So the output of this would be something like this. And this is literally just, there's only one document representation, so a line means a literal new line. It's not doing anything special. This is just the only representation for it. Now we want to consider a document with multiple possible layouts. We will view a document as not just a single string, but a set of strings. And this is achieved with the group operator. Given a document, the group operator adds one more representation of that document, one where everything is compressed onto one line, meaning all of the new lines are stripped out, or maybe they're replaced with spaces. So here's an example. This group has the text foo combined with a new line combined with text bar. There are two representations of this, foo space bar or foo new line bar. Groups can be nested, though. So when that happens, there are more than two representations of a document. So this group has 3 representations. There's the one top-level group, and that top-level group has these 3 representations. And so that's why when you start nesting groups, you start getting into more and more representations of what that code should be. So group is really the key to all of this. It gives the layout system boundaries for where things should break. So now we can implement a better layout function that chooses the prettiest representation of a document. Pretty takes an additional parameter, which is the preferred line. I'm sorry. Prettier takes an additional parameter, which is the preferred line width of the chosen layout. Pretty will choose the collapsed representation if it still fits on the same line within the line width that you gave it. Otherwise, it will choose a representation with new lines and recursively keep measuring groups. So here is back our tree code, the one that we had before. Now, the only thing we've added is we've wrapped it into a group. But because we've wrapped it into a group, because it's recursively going down, there are recursive groups, right? If you have a nested tree data structure and it's wrapping those into groups, they're nested groups. And so this would be the output of the pretty function. The top-level AAA node, the very top one that has these 3 children, was broken up into multiple lines because they didn't fit. But the inner node, the children nodes, were small enough for them to fit on one line. So now we're starting to see how we can measure something. If it doesn't fit, we break it up into multiple lines, and we recurse down it and continually measure the groups until we're done. That's basically it. For formatting code, we need to tailor this in several ways. Because formatting code is very different than formatting a data structure. In a data structure, you can pretty much just get by with something simple. Code, especially something like JavaScript, is super complex to work with. So we actually needed to introduce a lot more advanced operators that Prettier uses. Now we have group, concat, indent, but also conditional group, fill, if break, line, soft line, hard line, literal line. These things give you complete control over what is happening with the layout system. So there are some times where you actually want to break the inner group before you break the outer group and things like that. So this allows us to give that control. So here's a snippet of what Prettier looks like inside. This is part of printing arrays. There are so many things to get right with JavaScript code that it's a bit verbose, but I still think it's a pretty readable system. It's all composing these operators, and then the measurement system can take this expression of this layout and choose the best representation of it. So what I learned: Philip Wadler is the bomb. First. As a first thing. Second, JavaScript has a crap ton of syntax, and there are so many damn ways to combine them. But we weren't entirely sure if this would actually work, because we kept running into cases where this thing fit really nicely in this context, but then when you wrapped it in a function call, it looked terrible. But luckily, we landed on something that actually works really well. 3, way more people wanted this than I first realized. We really did not think it would be this successful. So how it influenced me, I see code differently. I just don't even think about it anymore. I see it structured, and as long as between these 2 statements, I just write the right kind of code, I don't have to care about how it's actually formatted. So it's drastically improved my ability to code. And that's all that I have to say. Thank you.